All right, so the first problem I want to do is in the equilibrium problems, number 5. It's a multiple choice question. You're given 4 figures with forces acting on a thin rod, and basically we want to know which one of them would have their torques cancel. But that is if the pivot point is defined as the center. So when you're looking at the first figure, you've got 2 forces here. Those are their respective directions. Next figure, here's our forces. Next figure, we have 3 forces. And that one's 2F. And the last one, we also have 3 forces. One here, and one here. Right now, our pivot point is defined right now as this right here. So right away, looking at these two, I can see that these forces don't generate torque here, so I'm not even worried about them. I want to see where the 2 forces are generating opposing torque, and that's when they'll cancel each other out, or whether they're generating the same torque, and maybe they won't cancel out then. It's always very tricky because it depends upon how you define your pivot point, because you can look at these things and you can't just look and say, well, which force is pointed in what direction, and let me look at the forces pointing in the other direction. What I always like to do is I like to say, what kind of rotation are they going to create? When I'm looking at that, I can tell how this object would rotate if these were the only forces exclusively acting on our object here. So looking at that, I can see these two work together. These two work against each other. These two work against each other. And these two work against each other. So this is the one where they do not cancel. And the rest of them, you're going to get a net torque of 0. Here, here, and even here. All right, so once you kind of get the hang of that, that ends up being a pretty easy problem to work through. The other problems that people asked me to go over was from the dynamic section, 3 and 4. So if we take a look at 3 has a picture of a disc, and we're given its mass, we're given its radius, and we're told that it's rotating about its axle. We're given 2 forces acting on it, and we want to look at 2 things here. So let me just draw my picture here. There's a disc, and it's rotating about that point. There's an axle. There's 2 forces acting on it. You got 125 newtons this way, and you got 90 newtons this way. Now, as we have seen here, the distance to pivot point is r. The distance to pivot point here is also r. So I'm looking at my torques here. I have 2 torques. Sigma tau. Let's see what it is. The radius here is what? 0.314. So if I want to go for my net torque, it's pretty easy here. This one is going to be positive. This one's going to be negative. Let's do the positive first. 90 times 0.314. Notice there's a 90-degree angle between the force and the distance to pivot point, so I don't have to worry about sine theta here. Negative force, you got negative 125 times 0.314. So net torque should come together pretty quickly. Let's see what we end up getting. I get something like negative 11. And does that make sense with our answer, K? Yeah, negative 10.99. Newton meters is the unit of torque. Now, if we want our angular acceleration, we're going to take the second law and apply it to that. Sigma tau equals I alpha. Now, we know that the mass of this thing is 24.3 kilograms. Based on that, we can get I. This is a disk. If you look at the shapes that we were given, a disk is 1/2 mr squared. So we have the mass, we have the radius, we can get our I value here. It would be 1/2 times 24.3 times 0.314, square that. I get something like 1.19. 1.19, and let's round that to 8 kilograms meters squared is our unit for I. Now we can solve for alpha here. Basically, sigma tau is negative 10.99. I is 1.198. Alpha is unknown, so we divide our quantities out, and I'm getting something like 9.17. Does that agree with our answer key? Not quite. Let me see, alpha. Negative 9.174 radians per second squared. Our answer key says 0.0917. So let me look at the problem again, see if I didn't miss something real quick. Yeah. I'm pretty sure I didn't miss anything. So it's entirely possible that when I made this answer key and made a slight mistake, I'll have to update that. This is our correct answer as far as I'm concerned right now. I'll take a look at it again and see if it actually is right or wrong. But I'm pretty confident in what I did here. Last problem. We want to look at the very next one. Problem 4. I guess it's very similar to this. It says, what constant torque in the absence of friction must be applied to the wheel to give it an angular velocity of 50 radians per second if it starts from rest and is accelerated for 10 seconds. The moment of inertia is 9 kilograms times meters squared. So if we're looking at that, it's kind of a numerical problem. All right, no real figures needed here, but let's take a look at all the information we're given. All right, so basically we want to know what kind of torque do we need for this. So I imagine we're going to be using sigma tau equals I alpha. It says that it starts from rest, so omega I is 0. We want to get it up to 50 radians per second. So there's omega F. Then we don't know alpha. We were told that it accelerates for 10 seconds. So I guess now we can get alpha, because if you look, we got 3 out of the 5. We have no idea what delta theta is, and I don't even think that's relevant in the problem, but you could even solve for it and it wouldn't be any harm to you. I, our value for I, is 9 kilograms times meters squared. So I grouped all my kinematic stuff here. This is dynamic stuff as far as I'm concerned here. Let's look at the kinematics. Let's get alpha really quickly. Going to the kinematics equations, that'll get me alpha. 50 equals 0 plus alpha times 10. Divide both sides by 10. I'm getting an alpha of 5 radians per second squared. Over to this, sigma tau equals I alpha. So it's a combination of a kinematics and a dynamics problem here. We can get sigma tau pretty easily simply by doing the 5, doing the 9, multiplying it by the 5. And I guess we will need a torque of 45 Newton meters. And just to cross check with my answer key, it says that the answer is D, and it looks correct. So here's our answer, 45 newtons times meters.